All right, this is going to be, what is that? One. I don't know why I'm forgetting it now. So Flare 11, FlareOn CTF 11 has recently finished. CTF 11. If you're unfamiliar, FlareOn is a CTF challenge, sets of challenges that people will go through to do different reverse engineering. It's put on by the Flare team from Google Cloud, or Mandiant, I should say, which is under Google Cloud now. Anyway, they put on year's challenge, so you can go through each of these and look at what the challenges are. FlareOn 10, it looks like it's the only one that's actually up on their current website, but FlareOn 11 is out. All the write-ups, the challenges, and everything should be out on their website, or things you can just go look at. I'm going to be going over the Checksum challenge. For this one, Checksum is this cool little program that is a portable executable. It's a Windows program. If we want to figure out some things about it, we can run die on this to get some initial information. Die is detected easy, which gives some interesting just attributes about the program that are particularly useful if you're interested in trying to understand some like standard overview information. So in this case, we see that this is running, this was compiled with Go 1.15 or higher, 64-bit actually. Yeah, so 64-bit. 64-bit was answering chat. We can see that the compile timestamp was put in 1969-12-31. So somebody mucked with the compile time of this particular program. We can get some general other file info here. That 64-bit, it's for AMD 64. It's for at least a Windows system. We can kind of assume that from the PE format. And then we can get some information about the entry point. We can look for this on, say, VirusTotal if we want to see if there's any hashes available. I'm going to move over that for now. Strings are a great thing to look at, and die actually has a nice little string interface. I think the cool thing here that if you aren't familiar with strings on Linux, or sorry, on, well, Linux, Windows, whatever, when you run strings here, we can tell already a lot of attributes about this. But there's some other strings that maybe are in little endian format, because a lot of the strings in Windows are UTF-16 little endian. So they got like zeros or null bytes in between each letter. Yeah, so it's kind of a weird format for just a standard big endian string parsing. So sometimes like these wouldn't have come up if we didn't actually do the little endian format. But coming back here, we can tell this is Go just from the Go build ID. Go build IDs don't give a ton of information other than, as an indicator, you could look for the same sample. You pretty much just using this build ID if you wanted to. There's a lot of nonsense in here. This is kind of standard binary things, but what we'll notice is there's tables of strings, or well, it may not look like a table, but it's a series of consecutive strings. So read, write, limit, count, save, error, token, format, and so on. These are generally formats or functions or things that you might see, or it might be types, or they might be full-on strings. And you'll start seeing as we keep going further and further, it gets bigger and bigger in like the length of the strings. And some of them are like not complete strings. Some of them are maybe libraries. If you're familiar with Go, the encoding library with hex. As we keep going, then we start getting, okay, well, there's full-on like references here to Golang org, and then the cha-cha-20 poly cipher, which is an encryption cipher or encryption library. And so we can start kind of also seeing there's maybe some error strings, and we'll just keep going. We can see some compiler information. So this was build mode, his exe compiler was GC. CGO wasn't not enabled for Windows. A lot of this is information we kind of already gathered. We can see a lot of runtime functions, so we can organize these if we wanted to figure out some general information about the program. I'm not too worried about that at the moment, but it looks like the symbols are in here, so it's not fully stripped, which actually should help us in analyzing this program. Analyzing a stripped Golang binary is kind of a pain in the butt. We can use Go resym to actually help with that, but thankfully it doesn't look like we'll need to actually depend on that. So yeah, we'll keep going. What I'm keeping an eye out for, and this is kind of hard. So normally when you analyze, say, like standard C++ malware, you might see specific functions or things or references to functions, and that tells you kind of what's going on in the program. Golang kind of has that, where you can be like, oh, well, it was using cha-cha. Okay, that might be a good reference. But for like Windows-specific APIs, a lot of them just sometimes get like thrown right into the binary because it's a statically compiled binary, or it's got some other weird references to things just because of the way that Go compiles its programs. So really, if you have these symbols here, you can make use of these to understand, if they're not runtime calls, but they're like that Go library call. We're looking at go.org, or if we actually do golang.org, we can look at all the different packages this thing tries to reference. So we see right now there's all these cha-cha ones. We see here there's some references, more cha-cha references, tons of cha-cha references, and then some information about the CPU. So there's definitely encryption happening in here somewhere, don't know where. But then maybe you might look at like for GitHub. Okay, well there's no GitHub projects that are brought in, which is good to know. So it's primarily using standard library calls. And if we go all the way to the bottom, sometimes there's some information that's just dangling at the bottom. Doesn't look like it, but yeah. So I mean, pretty much what we've gotten from this, there's encryption in this program somewhere, and it's definitely using Golang, or it's a Golang program, and the symbols are in here, so we don't need to actually look up and try to set up Go reset. We can get similar information from just the standard strings here. If we wanted to do a sort for unique strings, and then, I like to use bat just to make the output look pretty. We can get those specifics, or if we want like a specific length, I'm gonna look for anything that's of length 7 or higher. And we can get similar information this way. Now, one thing with Golang that you may or may not have already noticed, just by looking at these strings, the strings are in giant chunks. And the reason why strings that we're seeing here are in chunks is because they're not null terminated, which is problematic for analysis. You might say like, well, why is that? Well, usually when programs like IDA or Ghidra or name whatever is trying to identify where the string stops and starts, or starts and stops, it'll look at the reference first to say, okay, well, it starts here, and then it'll go all the way until the null pointer. The null pointer itself, or not the null pointer, but the null byte. The null byte will denote when that ends. Okay, so yeah, so it's looking for the null byte, and since the null byte is not here, we're gonna see in a lot of the decompilation, disassembly, any of the references to the strings is just long blocks of strings. So you got to take that into account when you're analyzing this, that what you might be seeing is actually not what the program is truly trying to pass along, or it's at least trying to pass along a reference, and the decompiler is kind of mangling that a little bit. So just keeping that in mind, I'm going to go ahead and close out of these, and what we're going to do is I'm going to use IDA, specifically 9.0. Start that up. I'm going to move that to this other window. And it already picks up. Okay, so this is portable executable. This is running x86. I mean, we already knew that, but this is going to use the meta PC to pull it apart, so it's not a big deal. We don't need to worry about any of the kernel options for now. I mean, we can poke at this if we want to disable some things. If you're familiar with IDA, generally you just leave most of this by default, unless you're probably dealing with bare metal or some really screwed up program. Go is, I mean, some might consider that screwed up, but I think for now we can hold off on meddling with this. It'll say a lot of the imports were destroyed. It's a Golang thing, unfortunately. But we can go ahead and just click past this and click OK and let it analyze. What's nice too, so IDA's gotten a little better, and it's a little good at identifying those function references and then organizing them into nice folders. So we can kind of just collapse this and take a look at what is going on in the program. There's a difference between runtime functions as well as library functions. And library functions are going to be things like your format prints. You might also get runtime prints, which are what the format print library references. Just keep that in mind, just that it's kind of like how most library calls work. There is a higher level interface that will reference a lower interface, and then from there it'll go ahead and perform the action. So we get format here. Here's the format library. Golang org, this is where we were seeing a lot of those cha-cha ciphers. Yeah, so we see cha-cha here. You also see the CPU referencing here. That might just be a Golang specific thing, like how it's looking at the CPU. This could be used for anti-analysis purposes, who knows. We see main in Golang, Main.main, or in this case Main_main is always the default main code for the program. Main.A, Main.b are some other defined functions that seem to be in this program that aren't always a common thing for Golang. But you know, there might be something to check out that's hinting maybe that it branches off of Main.main somehow. And the rest of these are some different types. If we click on any of these, it's kind of type equal. So this is maybe some like constructor equaling, kind of similar to how you can like define how two classes might do an equal or greater than less than to each other. Golang has like kind of its own way of denoting that here with the EQ for equal. So yeah, I think with that kind of sorted out, I'm gonna go ahead and collapse this folder real quick. It's runtime folder, and collapse this sync folder, collapse this internal folder, and golang.org. And I think that'll be good to start. Yeah, so we want to go to the main. Where we are currently is not main. We go here, and if we zoom out a little bit and look at this control flow graph, there's not a ton going on. There's a few different branches that's going on. So it can be a little bit more complex than like a standard main function that people might be used to. But it definitely, Golang has this interesting way of how it represents some of its like assembly, or also there's a lot of references. Again, like I was talking about strings, some of the control flow is a little weird, and how it jumps to certain places, and because it's a higher level language, more than say like C++, some of the references to classes and such are a little weirder in how they get passed around. So we're going to be thinking about the analysis for this in a similar way to how you might see C++ passing around this references or like self references to itself back to other functions. Or, you know, you want to think about like a lower level, you know, how might the print function be implemented? And we'll see a couple examples of that. I'll show you, just thinking of trying to keep an open mind about some of these, and it'll help hopefully make that a little bit more readable. But especially in the decompilation, when we're looking at just the assembly, we can see it jumps around a lot. Some of the sections aren't ever reached until, say, way later in what would be the decompiled code. But for now, I'm gonna go ahead and go to the decompiled view. I'm actually gonna break off this and right-click synchronize with the IDA view A and hex view. And what that's gonna do is it's gonna allow us to kind of sync, similarly if you've used Ghidra, where we are in the program, and it'll highlight it. And so I can kind of show you where some of the weird isms happen that, like, you know, that IDA kind of messes up, especially in the decompilation. I personally like to hide references, or sorry, the like the type references, typecasting. So I'm gonna go ahead and hide that. And then we're gonna go ahead and go to just the start here. There's a bunch of these variables. We'll see a ton that are defined. Like half of them are gonna be important. The rest are meant to just kind of pass around references in weird ways, and IDA just does not know how to deal with them. I'm going to collapse those for now. We see there's a lot of red here. Again, with a lot of the ways that IDA views Golang, it kind of makes some assumptions that some of these registers exist, or arguments when they're being passed to functions, partly because of the way like the function's expecting a certain amount of arguments, or it thinks it is. doesn't mean it's correct by any means, but it can cause a lot of the analyses of any individual function to break. So just keep that in mind. You see a lot of red, doesn't mean it's impossible to actually figure out what's going on. But let's kind of start with trying to figure out, I think, first how this program runs. I think it's going to help us the most with trying to explore this program, only because it's pretty easy. We can start figuring out, okay, well, there's some strings here where it'll check a sum, and then probably a format string where it's like a scanf, so it's reading in an integer value. And then if you use C or C++, right? And then there's this v31 that happens, which seems to be going to this Main.b. Not sure again what that is yet. We're gonna hold off on that. But then there's a comparison, and then it says try again. And then because it's returning early, that means it's probably leaving this main function and then exiting. So my assumption at this point is that based on the strings, we're saying, okay, well, give me two values that are going to equal this, and it's going to pass two values here. What two values? Not too sure yet. And then we're going to %d again, like I was talking about. So actually, let me back up a little bit here. The 21 and the 3, if we go back to this string, 14. If we take these strings, or like say, I'm just gonna grab this chunk here. Okay, I'm gonna Control C that, and the argument right after that's 3. If we go to IPython, I'm gonna set that string as that, and if we do x till 3, we get %d, \n, so new line. So that means the actual value that really matters here is this. But again, because I was talking about before, it's not null terminated. It just doesn't, it doesn't go past that. It pretty much tries to, it goes past that. It doesn't stop here. We can do a similar thing. We've been seeing like, okay, well, for some reason it stopped here. So there must be a null byte after this, like in that section of memory. And if we look here, actually check in hex view maybe. Checksum dd equals. It looks like there was a space here, and then it was able to discern that maybe. So kind of an interesting reason why maybe IDA just didn't clobber that one as well. But if we look at assert what the length of this is and make sure that it equals 21. Oop. And we see that that is true. So the assertion that this is greater than, or that this is equal to 21 is true, and then it's going to print that out. So again, I don't really know what these other arguments are for or how it actually works, but we can kind of tell, okay, it's going to OS file IO writer. It's probably writing to an output file. In this case, it's probably standard out. And then from here, this is the IO reader. So it's going to read to from something. In this case, probably standard in. And so that's where I'm getting kind of these assumptions from, that this is outputting some variables, not really sure what yet. And then it's going to output them. And then it's going to say, hey, did this equal? And if it didn't, try again. And it's going to kill the program. Or if it did, it's going to continue on. And then probably do something like, hey, that was good math. And then it's going to continue on. And this is a for loop. So this is going to happen a few different times. How many times? Well, it kind of isn't clear how many times, but we should expect that. There's this math rand here, and we can kind of check, like we might be able to go look up like, okay, well, how does this function work? If we go actually double click on that, it looks like it does some amount of calls to something. So it's this A1 here. It's using that and making a bunch of calls there, which is strange. And it passes a 5, which A2, it doesn't, it's making some decisions here. It's kind of hard to really make heads or tails of how that's happening, but some value is being popped out here, which is being used to compare whether or not we should break out of the program. And actually, this is the condition that should belong inside this for loop, which is kind of funny. If you notice, this is a initializing value. The Boolean condition that actually says when it should break is not in that for loop. And then it just increments I by whatever the value in v213 is, plus 1. So it's slowly incrementing that, and then here it's reassigning it to I. So this is another one of those weird isms that IDA sees because the Golang binary is just a little strange. If we look for the definite usage of v213, we really don't see it used anywhere else. So it's just a dead pointer at this point, or a dead copy of that I pointer. It's more just used to this increasing here. So we can ignore that. We can just say, hey, you know, I plus 1, and that's going to be that. So v221 plus 3, you know, we'll figure this out later. But there's some value it's going to iterate over. Not really sure what that initial value is yet. Let's go ahead and just try running the program before we get too much deeper into this. But again, the point of this little overview real quick of this initial portion is to think about, hey, there's a looping mechanism. We should expect to see it asking for checking of a sum between two numbers multiple times. And if we fail it, it should say try again. And if we succeed, it should say good math. And then assuming that we got it correct, it should go to the next iteration is kind of what I'm gathering. So I'm gonna go to my Windows 11 machine and we'll go ahead and run checksum. And checksum is gonna give us two values. We're gonna check the sum of those. I'm gonna go ahead and I have a Python window up here. Actually, this is me, I was testing it before, but 10049, I'm gonna go ahead and paste that. All right, we see it come up again. This is 1381 plus 1682. And we can automate this, you know, if we wanted to. We could probably set up something like Pwn Tools to automate the math here, but I'm gonna hold off on that for now. 9371, good math. And then it's gonna ask for this checksum. So notice like we didn't fail here. We haven't really got to this checksum part. Like where does the string come from? Not sure yet. Let's fail. It said not a valid answer, but if we do 2, it says try again. So there's a couple different cases here where it's saying not a valid answer and then try again. If we go look back at the code here, not valid answer happens here when there is some failure. I'm assuming this is a failure case because it says not valid answer and it wasn't just try again. Try again happens, it seems like, when some value doesn't equal our two values added together. So we might be able to assume that this is the summed value. And then this is like our value 1, and then this is probably value 2. And now we got to be careful with renaming these because it might get used later as not the same value, just because Golang sometimes reuses pointers or reuses references. So just keep in mind, you might run into that. So yeah, so we can assume that this is going to be the check when we decide whether or not we should return or not. After that, we did get good math, and then we got this next part, which was what was it? It was checksum, right? So checksum failed to read checksum input. So we're going to be looking for another like fscan again, probably, just because that's kind of the standard interface it seems like Golang is using to reading input. It's not just using like say raw syscalls or anything like that, or a difference between puts and sprintf and so on. So, or not puts, but gets, sorry. So we see here that it's creating a string and then storing it somewhere. There's also this offset, which is interesting. So if we double click that, it's a true, which is this huge chunk of stuff, you know, not really too cool. But it seems like this specific offset is actually the string plus 924. And this is where things get a little goofy. If we look at right below, IDA is kind of nice. It'll actually fix this offset for us and say, hey, this is printing out checksum. And if we double check, so v23 is getting passed, 232 is being printed out here to O standard out. Here's the value. We still actually don't know what the amount is, but when we go here, it's giving us some weird values. There's this 10h, 8. You know, how long is this? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So maybe this 10, oh, that's 16 in hex. So actually maybe not 10, like actually 10, but yeah, our type string, it's giving us some weird types. Again, it's saying that this is a string. So maybe this is just pairing it that this object here of type string is just a string to be used. It doesn't actually denote what the length of that is. This goes against kind of what we were talking about, where we were saying, okay, well, here is print string, and that's the length. Here's runtime print string, that's the length. Here's the format, and that's the length right here. Well, OS standard out, which if we come back to a standard out one, should be right after the definition or the reference. But the problem here could be that it's a reference to a reference, and that might be why it's being a little weird and not actually giving us the right value count, perhaps. It's kind of hard to say. I will say, after each of the strings though, there is this length here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 seems to be equal to the OA. So what this actually might be a reference to is maybe the number after it is the string length, which is kind of nice. Or this could be a length of, or this could be a table of defined strings that the program uses, and the value after that, or the byte after that, is that string length. We see noise, which probably noise with 2 exclamation points. 1, 2, 3, 4, 5, 6, 7. Okay, I'm gonna assume that at this point that's probably what that references mean, which is pretty nice. So that can help us a little bit with figuring out what this string is. So I'm gonna rename this as checksum string, and that's gonna go here. And this is checksum string object, because it's some string reference, right? Print out, file writer, standard out, and it's gonna print checksum. We're gonna create another string, which this looks to be something that's being read in now. So we're gonna be reading in a string from the user. How long is that gonna be? It's a little hard to tell. It's a pointer string, which again, this type reference doesn't actually give us how long it's gonna read. But if we go to like Firefox and we look up, what is this, Fscanf? Yeah, so Golang Fscanf. I'm gonna go to this format package. We're gonna go to Fscanf, and we see that it's the reader, the string, and then any. So it doesn't actually seem to have a particular length. Like it's not anything that's defined, at least immediately. So might be useful for us to at least know that this is an unbounded length at the moment. But it's going to be reading into this v31. So this is going to be our user checksum string. And we kind of have a similar situation here with Main.b again, which looks to be, I'm just going to rename that as error func. You know, it's going to be an error function. But it does an interesting thing. Let's actually go investigate how this function works real quick so we better understand what's going on here. It checks if result is something non-null. Looking at fscanf again, it should return the number of items successfully parsed, new lines in the inputs. So the return value for this, I'm assuming, is the number of items that are scanned. But maybe that's not how the actual function works. Like in like at the C level, you know? Because what we should expect here, v23 is actually OS standard in. So maybe this is a way that OS std in can define like, hey, we failed to actually read from that input, and that's it failing there. That could be what's happening, because this error function seems to be something that is just a reading issue. So this actually could be a reference to say, hey, you know, we failed to read that input value, which we kind of saw here when we were like reading in, oh, where's that? When we were reading in this, failed to read checksum input. So kind of interesting, I guess, where, you know, when we go to this error function, as long as it's a non-zero value, we're going to go ahead and return with an OS exit. And this value is going to be OX deadbeef, which is pretty cool. But it's going to assuming like this is how this works, it's going to, oh, there we go, syscall exit, runtime exit. It's just going to flat out exit the process. Fantastic. So this is a full-on like error crashing, which is what we saw when we were doing that initial checksum. It failed to read the checksum. It just fell out. It didn't crash, but it exited. I didn't grab the exit code, but we could grab that if we wanted to. And then let's see. So the not a valid checksum here also happens, where pointer again is oh wait. Hold on just a second. I think I went a little too far. There we go. So yeah, reading check. So for the user checksum string, it passes v42, which is that OS standard in again. So it seems like that might be where the errors are being passed through, or like where the error codes are being set if it fails to properly parse that value. So we can just assume that this is like the, you know, our error. Actually, I'm gonna hold off on that because I think this is also different up here too, right? Yeah, v23. So if we name them different things, you know, we just need to make sure. Let's see. We'll do like that. All right. So if there's an error, then it's gonna go ahead and print not valid answer. And notice it doesn't, so this is argument 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So A5, it doesn't seem to really make use of doing anything. Yeah, there's some parsing here that's done. I'm not going to dive into that. That seems a little pain in the butt to actually reverse. But assuming that this is going to do some parsing, it's going to print out some things and say, hey, this failed. And that happens down here too. So failed to read checksum input. It's going to give us the error number here. Fantastic. And then we do string to slice byte. So string to slice byte is actually something that you might be familiar with if you've ever done any type of byte manipulation or data manipulation inside of Golang. But this is just effectively converting strings to a byte string or to byte array or byte slice. You know, Golang, it's not arrays, it's slices. So that's what this looks to be doing. It's passing it pointer to the string, right? And then the length of the string itself, and then the size of the string, which is 30, which is interesting. I'm assuming that this is maybe the size, but let's do a little bit of validation. Let's see if we can find Golang string to byte slice. Convert between byte array slice and string. So, okay, so this is converting the string, which looks to be a hidden function. It's not even like one that is actually maybe done, just more like deliberately. So like this is why maybe it's a runtime. So string to slice byte. If we look up that, this might be in the source code though. Yeah, here we go. So in the string go library in Golang, string to slice byte is right here, where it's going to give us the temporary buffer and then the string that's being passed to it. A little bit different than maybe what we were, I think, expecting, but that's fine. It's passing the string. This might be some optimized portion of it, but we would expect that this is probably doing some sort of movement. It's just converting it to a legitimate byte. In this case, I would want to see if there was any type of reference, and this is actually the Go. This is not the C portion of it, which is fine, probably. But hard to really pair up what these references are maybe talking about. V209, I don't think is anything yet. Does it get used anywhere? Maybe this is also the error or an error. v209 doesn't really seem to get used anywhere. We can actually just X on that and see if there's any references within this current code that we're looking at, and no, does not look to be the case. User checksum string gets passed to it, so I would assume then the reference or the output here is the we could say user checksum byte string or byte array, right? So it gets passed. This gets to 211. 211 goes then here, and it panics. Don't know what 211 is yet, because 211 is seemingly nothing, but it's from v55. So again, don't really know what that is yet. Pointer goes to v56. v56 is getting pushed around to other places, but pointer looks to be the string pointer. So this is p string, which p string got defined here when we read in the user data. So this is the user checksum string. So let's just name it. We could say checksum string pointer, or checksum string pointer, v56 and v60. So it's doing a hex decode, which is interesting too. So let's see. Golang hex, or encoding hex decode. There we go, hex.decode, which takes in a destination and a source. So checksum byte string and the checksum string pointer. So string to slice should have converted it. But checksum string pointer. Oh, this could be reusing that pointer potentially. This is also interesting too, that it resets it to 24. Again, this is that reusing of variables. It's super weird. So it may not be worth actually using this. This is another error function, or an error output. For now, you know. v56 is not immediately used. v60 to v12. All right, encoding hex string. Yeah, so I mean, I'm assuming that this is going to decode, and if it's following a similar convention where it's destination source, this is the destination, this was the source, and the source is the pointer, destination's that one, which is still strange, right? So strange that it's still, yeah, it gives the checksum string, which converts it to, you know, it's still the structure, right? The string type, but then converts it to the byte string. And then what we're seeing here is it's decoding it maybe back into it. I don't know if it's making, oh, it might be trying to reuse that pointer. That could be actually how this implementation works at the lower level. Where were we? How this works at the lower level. I know we were seeing the string runtime go slice, string to slice byte, but maybe at the lower level, this is like, it'll overwrite to the location, reuse the pointer, or reallocate it to something else. And that's what's happening here. Because I mean, we see this being used v76 right here with a key. It seems to be very interesting. But it's going to decode that. And then error func say it's not valid if we couldn't decode it. So this is, you know, if it's not a valid checksum, this is meaning that it decoded incorrectly. And I think that this is actually meant to be of length 30. It's kind of my thought at the moment. Just because like this is really conspicuous. It's kind of weird. So maybe this slice byte should be of length 30. And it's hex, so 15 bytes. So we should have 30 zeros or 30 something. So I bet you if I go back here, I'm gonna rerun that checksum. I really need to make a program that just evaluates this. All right. Should be the last one, I think, right? No. How many did I do before? I did 1, 2, 3. So this is 1, 2, 3, 4, 5. I wonder if that 5 has the significance of like it's like an upper bound, so 0 to 5. So this should be the last one. Maybe not. Holy crap. Okay. I guess it's a lie. I don't know anymore. Okay, here's the checksum. So now what I should be able to do is we'll just do 0 times 24. Oh no, sorry. 30. Yeah. Because it's like valid hex, right? Okay, cool. So we didn't get a bad checksum. So now it actually passed that, and it got to this other one saying maybe it's time to analyze the binary. And that happens down here, another error func when v79 occurs, which is, looks to be for bad key length maybe. All right, so then this is going to be coming back here. We see that we've read it in the value. It's making a slice v56 here going into v70, so that's the reference. Based on what's going on here, so this is that contract I was talking about again, where if it reaches a certain length, it's going to go ahead and break. For some reason goes over a length, which this is 24. So if for some reason jumps over that, it's going to panic, which is a more just trying to make sure we're not out of bounds reading, right? But v76, checksum byte string. It's a key for some reason. This is a byte string type. We hover over this. So it seems to be what it's doing is it kind of is casting it into this byte string, which that could be what's happening. I mean, let's go look at like what this cha-cha poly struct is. So I think we can go look at, see, Windows and structs. Where are you at? Our view, sorry. Open subviews, structs. Why am I being, local types? Oh my gosh. Okay. It's probably in this one. Actually, I should be able to cha-cha. There we go. Oh, okay. So it's just a uint reference to a key, or uint32. So, does that mean it's 32 length array? Is this a reference to one? I'm guessing this is the size. So like this entire thing should be of, yeah, it looks like the entire size of it. It's not a pointer, otherwise it'd be 8 bytes, but it's 32 in length. Kind of interesting because I think the string that we read in was, let's see if it failed to read in, if it was like greater than that, or wait. Maybe not. Maybe it doesn't matter. I mean, I assumed it read in 30, but maybe it doesn't care. Let's run that again. Maybe as long as it's like a valid hex, it just will read it in. It's actually a good point. I don't know for sure. Okay, so we just do 0, 0. Okay, so it doesn't matter the length, I guess. This 30 doesn't matter. So it seems like though, it needs to be 24. It's gonna read over 24. And so this check right here for J, V75, V22, V60 is the output of this hex decode. So this is where it's going to break out. And then it's going to check actually if the length of that, of v212, which was v60 of the hex here, if that equals 32. So we actually need to put in a length of 60, which is kind of also interesting. And it's going to do this error function. If, oof, there you go. It's going to do this error function here. If for some reason, see, v80. Ah, I see, okay. So this guy right here, it's a non-zero value, right? But this meant that is bad key length. So it's gonna go ahead and say, hey, that's a problem. But if it wasn't, we actually shouldn't get, oh shoot. We actually won't know where we land here, will we? But it'll get a pointer here. Or not, actually. Interesting. Okay. So, I mean, it's strange because this actually means that, so it creates a new object of type that. If the cha-cha poly here doesn't equal the uname byte string, I'm guessing because this is going to be also another, like these are both cha-cha pointers. If it doesn't equal that, it's going to v20, it's going to mem move, and it's going to copy all the data over of length 32. And then v202 is just going to equal that. Okay, it's not bad. And then it's going to go ahead and AEAD, so v79, which seems to be, this is v187, which might be the reference for the function it's going to use, which looks to be what's going on here. Whatever that is. So we go here, and then it's doing an offset of 4. Okay. Is that this one? No, it's gotta be this one, right? It's a public function. Okay. Well, we'll say it's calling, so this is the itab, or the table, crypto cipher EAD. Cha-cha poly, so this is the poly pointer. This will not go through. Main encrypted flag data. So that's definitely encrypted flag data. Other one here, and another another piece of data. So not really sure how these are used yet, but the encrypted flag data is right here, which is actually a reference to this data, main go bytes. However long that is, not really sure. We go back here. Doesn't fully tell us, but maybe it's these bytes. They're too similar. So I'm inclined to think it's this data right here, right? So what we can do is we can just kind of keep going through. We see where this gets used. It's passed in down here to making a slice, where we're making pointers. 2 times something, 2 times something, and then making the pointer. Pointer. Let's see, time to make the binary, digit reset, or digest reset, sorry. So error func after this function, v203 pointer, v214 pointer. So this is making a new structure. We're gonna write this digest of v198, which again, this is kind of like, oh, this is an initialized object. I don't think v198 ever got initialized formally, but it's from this v1 pointer, which, you know, where did that come from? Not sure at the moment. Yeah, so we'll do a while loop here. This while loop has some of these panics in there. Again, we're going to ignore the panics for the time being. It's going to iterate over all of the indexes, which v01 sorry, v102 is the iterator. So we can just call this iter. v101 is referencing to v202, which v202 is a reference of v90, which v90, I don't think we know where v90 is, do we? Okay, where are you at? Ah, it's just that. So, yeah, so v101, it's gonna pull a value from there somehow, and it goes into v103. v103, it looks like this is gonna be iterating over this array here, and I'm assuming v103, this is like decoding the key basically. If I had to take a guess, you know, as we're coming here and actually pulling out of R8, R8 is V80. V80 is RAX from the crypt digest probably, or it's like the response code from it. This could be iterating over the digest, or if I had to take a better guess, it might be iterating over the key or over our input, which based on this, I think our input is the key, you know? So 32 byte key. It's going to iterate over that. V97 is somehow being used, which doesn't look to really be used for some reason, but I think this is an offset somehow. So R10 is how this is being pulled into, and then EI right here. So these are the same guys, and it's pulling over R10 plus RDI, where R10 is this and RDI is the offset, and that's where the shift right is. So whatever the value that got put into here from R8 plus RCX. In V99, you know, while V99, which is the index, and then it's gonna keep increasing this guy, which doesn't seem to actually be used for an error anymore. Again, reallocating variables, which is kind of a pain. But this looks to be like a destination pointer of sorts, or not, maybe. It definitely is an offset because it starts at 0 and it's increasing each time. It's increasing by 2 actually. So this could be writing out a hash value, like this could be the digesting, if I had to take a guess. So it could be like it's outputting the hex, because then it slice byte to string, so it's converting something to a string, and then we're passing it to Main.A. So we're taking the pointer and then our p string in v104, which v104 is a v95, which v95 again was this guy. And then we come here and we make a slice. And oddly enough, for v5, which is v9, this guy, these are the same. We're having a similar issue here where it's actually loading an offset, which is FlareOn 2024. Again, if we come back here, it's kind of hard to tell actually, but it should be FlareOn 2024. We see bad here, but it's again just right next to it in the strings. But we see R8, it's getting put here, R8 plus RAX, which again, this is the reference V18, believe, or at least just this reference of R8 plus RAX. So this OX, if we actually turn this into a hex, should be the same BF4. So BF4 is right there. It just optimized it in a weird way. And then it did the offset, and it's going to increment over that. So it's going to increment over FlareOn bad. Again, it's going to check if it's greater than OXB, which, you know, coming back here, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which is OXB. If it's greater than OXB, it's going to break. We actually should have seen one where if it is equal to OXB, it's going to panic if it's greater, but if it's equal to, it should have broke. But I think because there's actually a condition here where it's doing a while loop and it's going to break when it is greater than that, it's going to leave. So shouldn't have to worry about that. But what is this doing? This is taking iterator. It's looking at v15, which is again of v26, which is of the argument that got passed to this. It's gonna pull value, so v19. v19 is gonna be XORed with FlareOn 2024. And then we're going to encode a value here, which in this case, v9, right? v9 to v20. v20, v9, I'm gonna encode here. If v20 is equal to 88, which I think is kind of hard to tell. Maybe v9 is like the length. So a2 might be whatever the original string, like they're just making a slice, or the size. If it is equal to 88. 88 divided by 2 is 44. Not really good equal types. It's kind of strange nonetheless why this is a case. But if it does, it'll return back the mem equal. And then if that mem part is equal, we'll come back to this Main.A here. So we got, this is not an if statement or a for loop. So v10, 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 if not v10. So in these error cases here, it's gonna go ahead and seem to, maybe it's time to analyze the binary. This is a failure state. But if it does succeed, it's gonna use caster. It's gonna grab the flag, and then it's gonna write the flag. So it's actually creating the string here of whatever the path is. I'm guessing OS caster to 203, 203 length, v17. However, it's gonna find the full path, and then it's gonna write it to that file. If you look at OS write file, so first one should be the name, which I'm assuming is this guy, right? Yeah, so the first one should be the name. And the data, so v17, this is the data. v0203, that may be wrong, potentially. What about v191? Yeah, it's supposed to be the file mode. I think 420 is the file mode. IA4. If you look at the file modes, yeah, so here's the different modes. I'm guessing it's going to be a create, or append, or, well, this is for Linux. I don't know about for Windows here, if it'll show it differently. Windows? Yeah. Well, we can assume that this might either be the length of the, this could be also the length. Yeah, I didn't think about that. Was this runtime or is it OS write file? So this could be, so we're gonna open the file. That's the perms right there. Or not. And then writing the file, which is done to v9, v16. And v16 is the pointer to the data. So 0, 1, 2. So the file locations 1 and 2. And then 3 is the, so 0, 1, or A1, A2, A3. A1, A2, A3. So this pointer here in v203. So I'm gonna look for where the pointer got set. Here. So v203 is this guy. And it's not the encrypted flag data, is it? It might be, actually. This 214 got set here for v203 pointer. But it's 2 times that. Yeah, that's very possible that this is v186. So this is that cryptor cipher. This is definitely it, like analyzing the key. Let's see. So first off, we want a key of shoot, well, how long was it? 32. So we need 64 zeros. Let's go ahead and do that. See if we can get there. I think it's gonna still give an error. Oh, shit. No, this is like super invigorating. Oh my gosh, why did I do that? Okay, there's the checksum. All right, so we're just gonna print or do 0 times 64. Damn. All right. Again, don't know where that's landing. We may have to do some debugging. Kind of want to avoid having to do debugging. And actually, with debugging, we actually might be able to avoid doing all these like checksum checks. Just because it's kind of stupid. But let's see. So there was one of these error cases down here. I think it was this one, right? So this is where it failed, didn't equal the right amount of data, and got here. So we actually don't know if this was the equal case. So that's something that we can do here. We'll just tag like, hey, this is gonna be this one. Okay, so coming back down. After we decode this cha-cha here, it's gonna grab the encrypted flag. It does something with it, still not sure fully how it actually uses it. It's gonna make a slice of bytes. It's gonna iterate over it using this, create another slice, and then it's going to check and make sure that v105, which is the slice to byte string, is equal to the string pointer. I'm assuming this is doing some sort of encoding. It's like changing it to hex, or at least making sure that it does equal the same thing. It's kind of hard to tell, I guess. But if it does equal, then it's going to go ahead and call this Main.A function. It's going to pass in the pointer. We're going to assume that it hasn't been fully manipulated by whatever was going on in this the cha-cha cipher here. But when we get to Main.A, this was interesting because there's kind of this pointer v18. V18 gets used as kind of an offset, I minus, and then it's some shifter. If we do this in Python, let's see, where is, see if I can find my window here. So I'll do I equals 2. Oh. So that equals 2. I equals 3. 3. So there's something funny going on here. I think this is just an optimization-ism. Some weird goofiness that's happening. But it's taking whatever the value is here. It seems very complicated, but definitely not at all. And then for each one, it's going to iterate over this and XOR it with it and store it somewhere. So we can assume that whatever the data, then after it gets base64 encoded in here, is just XOR base64. Or sorry, it's just XOR data out of here. So we, from base64, do B64 decode. And then I'm gonna, from Pwn tools, import XOR. And then I'm gonna XOR that with Flare 2024, which I think was the right one, right? Oh, FlareOn. So actually, let's just copy that. Make sure I got everything correct there. FlareOn 2024. And that gives us this hex. That was like almost verbatim hex, which is kind of cool. So we can come over here. I think we might be able to actually just use that because that looks to be exactly like a checksum that it's looking for. See that. Doot. And then this. And then we'll just keep going. We're almost there. One more, I think. Okay, now we go back, get that checksum value. I think it's gonna be this one. Okay. Now, the other thing that we need to find is where this file actually created, or where did this actually create the file at? When we're looking here, because I'm assuming that it's writing this JPEG, this real FlareOn flag JPEG. We can just search for that. It's also using user caster. So if we look up what this function does, Golang OS user caster. Let's see, user caster. So this will give us turns local app data on plan 9. Or wait, no, yeah, Windows. So let's go to that. And there's the real FlareOn flag. If we double click it, the math do be mathing. There we go. We're not gonna edit it using AI, that's for sure. All right, thank you.